What does forward kinematics mean? That word has a lot of significance. You'll hear it a lot of times in this course and perhaps outside. So this literally means that given joint angles, uh, compute the position and orientation of the end effector. Okay, so let me just demystify this. A manipulator is like, think of a manipulator is like your hand, right? It has a linkage consisting of links. So the top part of your hand, the second link, and then they're joined through joints. So what this is saying is, if you're given, let me just try it here for people who are on Zoom. Here is a manipulator. So you can think of that as your hand. These are the links of the manipulator. This is the manipulator. There are joint angles, theta1, theta2, theta3. These are the thetas. And then if eventually what you want to do with the manipulator is you want the end effector. This is the end effector. So that is this piece. You want that end effector to grip something. So in order to be able to grip something, this manipulator, you need to know what is the position and orientation of the end effector. So this is x and say theta. So position orientation would be x and theta. So what is the orientation of the manipulator so it can go and maybe grip an object? So very useful thing, right? So if you know this, then you can do great things with a manipulator. So what we'll do is we'll get started with a simple 2 degree of freedom manipulator. We'll derive the forward kinematics, which is the end effector position, and in this case only position, given the joint angles. So here is here, let me so link 1, link 2, let's say end effector. Okay, now the first link is grounded, connected to the ground. So you always show the ground with this kind of a symbol. This basically means it's a pin joint, and there's a pin joint here. It's usually just shown with a dot, just so I'll avoid clutter by doing that. Okay, so we are given theta1, which is this angle. And then there's a way in which we draw this in robotics. We always extend the first arm, okay, and then find the angle between this and the second link. So that is how it's usually represented. Okay, so now let's get to work. Let's see how we can compute. Let's call x, e, y, e. So here we're interested in computing XE, YE. Okay, we're given theta 1 and theta 2. Sure, yeah, we need the lengths, absolutely. L1, L2. Okay, now let's, I'm going to put a few, like pretty much name a few points so that will help us to uh, then use that to get the frames. So let's say that this point, the first point over here is O, this is say P, and this is Q. But then let's just call that E because we call this XCYE. Okay, so uh, so given this, we need to find XCYE. Well, you could say we know how to do that. We can use trig, right? So here is how you save it for later. Let's look at this. Let's do it with just trig, just to show you that it's possible to do it without any complicated equations. Just that it's not transferable to more complex system. So you can see that that angle here, which I'm going to show here, is actually theta 1, right? Because this line is straight line. And then if you want to find, so method 1 trig. So if you want to compute XC, so the x coordinate of this point, so let's call that is this that point. So you just drop a perpendicular right here, and then you can see that it is L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2, right? This will be L. So when you drop the perpendicular, you get L1 cosine, and then if you drop a perpendicular for this length, then you have L2 cosine theta 1 plus theta 2. It's not very hard to see that. So L1 sine theta 1 plus L2 sine theta 1 plus theta 2. Okay, so that's like the obvious way to do it, but we'll use the formulas we develop because we can then not have to rely on trigonometry. And we don't want to rely on trigonometry because when you want to make a computer do it, the computer cannot see it graphically the way we see it, right? So this is good for an exam, but it's not good for a computer. So we want to automate the process of getting these formulas, and that's what the homogeneous transformation will help us. So this is the trig way of doing it. Let's do it the other way, which we've developed through the formulas. For that, what we need to do is start with a base frame. So let's have a base frame which will be fixed, it will not move. So let's call that O, XO, YO. Now, when you want to attach frames, what you do is attach the first frame, the x-axis, the first frame to first link. The first link is here, so I'll attach x1 here. I'll drop a perpendicular like this and call that y1. And this frame here is clearly O1. Okay, so O1, X1, Y1 is the first frame. Then we go to the next link right here at P. To the same construction, we have X2 along link 2, and then we have Y2 at 90 degrees to X2, and then we'll call this point O2. It's also called P. Okay, so PO2 is the same thing. Okay, that's all which is needed in order to fix frames. Once we have frames, which we realize there are two frames. So we have OO, XO, YO. Then we have O1, X1, Y1. And then we have O2, X2, Y2. Okay, so let's get started and get what we need. We need the position of E. This is of interest. We need this position. So what we'll do is we'll write a formula for E in the base frame, right? And what we've seen before is, if you recollect, it's C0 is H1 0, H2 1, so on, Hn n minus 1. N minus 1 Cn, right? This is the formula we derived some time back. I'm just going to apply the same formula. So if you want this, what we do is E0 is, so to get from here, this E, by the way, is in frame 2. So I will write it as E2. So I need to go from E0 to E2. So clearly I need H10, H21, E2. Okay, so let's try to write these things down. What is E2? Okay, what is E2? E2 is the position of point E in frame 2. So in frame 2, right? So frame 2 is what? It's basically this frame, O2, X2, Y2. So we see that point E2, which is, let's put an arrow there. This is E2. Okay, so this is the point E2. Show the big blob. Okay, so its coordinate you can see in frame 2 is simply, the point is simply along the x2 axis. So if it's along the x2 axis, its coordinates are simply L2, 0, 0. You should put L2, 0, 1. Okay, so this is the coordinates of E in frame 2. And then this is the placeholder. Remember, we had a placeholder for the homogeneous matrix because by default, position of point E has only two things, X and Y, but we need that one because homogeneous matrix is 3 cross 3. So that's the position of P2, E2. Okay, so what's H1? So going by the definition, it's going to be R10, 0, 0, 0, O10, 1, right? So R10 is cosine theta 1 minus sine theta 1, sine theta 1, cosine theta 1, 0. This should be, sorry, two zeros. And then O10, which is right, this point. So it's the coordinate of O1 in frame 0, but we know that O1 and O are at the same point. So it's going to have coordinates of 0 and 0. And then this will be 1. Okay, so this thing, different color. This thing is here. And then this part is this. Okay, now we need to write H2 with respect to frame 1. That will be R21, O21, 0, 0, 1. Okay, so R21 is basically how frame 2 move with respect to frame 1. So clearly that we only need theta 2 in order to describe that, right? It's because O1 is, you can see, it's tilted. So this is going to be cosine of theta 2 minus sine theta 2, sine theta 2, cosine theta 2, 0, 0. Okay, now we come to O21. So we need to compute the position of O2 in frame 1. So O2 is this, and we need it with respect to frame 1, this one. Okay, so you can see that O2, in other words, you need to find how O2 is placed on frame O1, X1, Y1. You can see that O2 is along the x-axis, X1, So its coordinates are going to be simply L1, that is along the x-axis. So L1 along the x1, 0 along the y1, and then there's a placeholder, but not for this one, but otherwise there'll be a placeholder. So it'll be L1, 0, 1. You might want to make a note of this. This is long x1, and that's why it's that what it is. Yeah, so that's all to it. You can see that we have everything we need. H1, H21, E2. We only need to find E0. So let's sub it in and see what we get. E0 is H10, H21, E2. This is cosine theta 1. Zero, zero, one. Okay, and then we thought it was L 1, 0, 1. And then I think this was L2, 0, 1. Yes, right. So we have a formula now by doing this homogeneous transformation. And we also obtained the same one answer using trig, which was here. You can see this answer here, L1 cosine this thing. You can check it compared against this one. It's the same thing. And then if you look at the other one, this one, and you compare it against this one's the same thing. So this gives you the same answer. Of course, we did a lot more work to get the same answer. But the good thing about this formula is it's all formulaic, which means that you can put that in a package like Python and get the answer. There's a symbolic counterpart to Python. So just like you could do symbolic computations in MATLAB, you can do symbolic computations in Python. We'll do that a little bit later, but you can get this answers automatically in Python. You don't really have to do it by hand. What we'll do is we want to be able to animate the manipulator. It's a very important skill because that's how we can debug. It turns out that to animate this manipulator, okay, so for animation, we obviously need point E, but we also need point P. So if we have point O, we have point P, and we have point E, then we just draw a straight line from O to P, and then a straight line from P to E, and then we have a animation of the manipulator. So we also need to compute the point P. Okay, so I'll write down that formula. I will not walk through the details. If you want to do the same homogeneous transformation to get point P in frame 0, it will be H10 P in frame 1, P in frame 1. If you go back, look at this. We want to find position of P in frame 1. It's the same as O2 in frame 1. You can see that point P in frame 1 in this frame is basically, it's along the x-axis, x1 axis. So its position is just L1, 0. So this is going to be L1, 0, and then 1 is just a placeholder. H1, 0, we've computed that before. It's cosine theta 1 minus sine theta 1, sine theta 1, cosine theta 1, 0, 0. And then there's O1, 0, which is going to be 0, 0, 1. Okay, so what I want you to do is put this H1, 0 and P1 in that formula for P0 and show that you get L1 cosine theta 1, L1 sine theta 1, 1. Okay, so the coordinates of point P are the first two. This is the x coordinate, this is the y coordinates. It's easy to see that using trig 2, right? So we've got the point O, which is 0, point P, which is the formula I wrote down here, and then we have the point x, c, y. So we have O, P, and E. All we have to do is join a straight line, and we know how to draw a straight line. So here is, I'm going to give all this code to you, but I just wrote a code which does exactly that. I define the lengths to be the question. So we have lengths L1, 1, I just put 1 and 1. I just put some angle, theta 1, theta 2. Just to make my life easy, I used C1, C2 to denote cosine theta 1, cosine theta 2. You can see when I write this, something like this, O01, it means that it's the position of point O in frame 1. We put a comment here. Position of OO in frame 1. And then this is going to be position of O1 in frame 2. So I define H01, H12. You don't really need H0. Well, H02 is H01, H12 if you like, or I just did not use that notation here, but you could multiply them and keep that ready. So then I have point P0, which is this formula I wrote down, H01, P1. And then I can get P from X and Y coordinate. And then Q2, here I used Q2 is the same as U2. Q is the same as E. E is the end effector. I just use Q in my in the code, but it's basically same as E. So H02 or H1 times H10, H21 times Q2. That gives me Q. And all I do is draw two straight lines. One is from O to P. And if you remember, this is the syntax for drawing a straight line. And then draw a line from P to Q or P to E. And then label x-axis, just make it equal axis, and then see what shows up. So scored. Okay, so it's just some angle. So let me, 0.5, and then it was 90 degrees, the second one. So that's how you do forward kinematics, given the joint angles. So given theta 1, theta 2, you compute the end effector position. So here the end effector position is Q. So if you want, you could also print it out. Print Q. Here's the output. Since it's not printing it out. But try reopening it. There's some problem. Let me just try running it again.